What's up, nerds? It's that time of year again. We're all studying for finals. We all want to kill ourselves. But the good news for you is, instead of killing yourself, you came here, and that's character building. So this is a review series for Cal 3. I'm going to do like one video per concept. Hopefully I'm going to get over 10 minutes on most of them, because I want the monetization. So let's start off with vectors. Okay, so hopefully all of you have already heard about vectors. Either you learned about them in high school or you watched Despicable Me. But just for review, what a vector is, it's a mathematical quantity represented by an arrow with a direction and a magnitude. So there are a few reasons why we use vectors. If you're a computer scientist, then a lot of the times you'll just use it as a way to list numbers together. If you're a mathematician or a physicist, then you use vectors to represent principles of space-time. We're going to stick with the math way, that way it's easier to visualize and then we can understand it. So in order to know whether or not we're dealing with a vector when we're doing a problem, we need to know what the fuck it looks like. So let's start with the easy shit. If you have a variable, you want to know whether or not it's a vector, oftentimes it'll tell you, because there's going to be an arrow on top of it. So because we're all beautiful mathematicians and physicists instead of dirty fucking programmers, and we want to make sense of the universe, we're going to define our vectors in terms of spatial coordinates. So what that means is that every vector is going to have one numerical quantity for every dimension of space that we care about, right? So because we're in Cal C, everything we're going to be doing is going to be in 3 dimensions. If you're working in a lower level math, you're probably going to have 2 dimensions. If you're studying fucking string theory, you'll have like 10 dimensions. So what you're seeing right now is a vector in component form. What that means is you have these angle brackets, and inside them you have one number for each spatial dimension. Very simple stuff. So another form that you'll see vectors in, maybe more common, unit vector notation. The key difference is that each numerical quantity has an associated direction. So that's a lot of big fucking words, but basically all you need to know is that I represents the x direction, J represents the y direction, K represents the z direction. So let's go over some operators now. Here we have a vector with some... So let's go over some operators now. Here we have a vector with some arbitrary constant, ai plus bj plus ck. Let's say we want to learn the total magnitude of this vector. What we would do is we would use the Pythagorean theorem. You learned that in 7th grade. You're a college student. You should know that now. A squared plus b squared plus c squared equals magnitude squared. So we just take the square root of that, and then we get our magnitude. Fuck yes! So magnitude is the only operator that uses one vector, but there are other operators that use 2 vectors. Let's say we had another vector w with m in the x direction, n in the y direction, and p in the k direction. I don't fucking care, I'll keep that. So what can we do with these 2 vectors? There are quite a few things. We can add them, we can subtract them, and there are 2 ways we can multiply them. One of them is called a dot product that returns a scalar. One of them is called a cross product that... Stepped on a piece of fucking... One of them is called a cross product that returns another vector. Now just for the sake of why the fuck not, we're going to go over addition and subtraction. So if we want to find the sum vector between b and w, what we want to do is add the components in their respective directions. So a plus m in the I hat, plus b plus n in the j hat, plus c plus p in the k hat. Now if we were to subtract them, we would basically do the same thing, but subtracting, of course. Now that we've gotten the small brain shit out of the way, let's do... did I just fucking voice crack there? Now that we've gotten the small brain shit out of the way, let's get into some multiplication. So our first method of multiplication is a dot product. Now one way we compute that is we take the magnitude of our first vector, multiply it by the magnitude of the second vector, and then multiply that by the cosine of the angle in between them. That's the fucking hard way, and we're not going to do that. The real way we compute this is we multiply the components and then just add them together. So a times m plus b times n plus c times p. And you'll notice that there are no hats here because this product returns a scalar and not another vector. So our last operator here is the cross product. It's another method of multiplication. So what we do here is we make a matrix out of each component. We'll label them I, j, and k. So we start with the first vector a, b, c, and then we go on to m, n, and p. And of course this returns another vector, so it would be something in the I direction plus something in the j direction, and then something in the k direction. So how do we find each of these components? So let's say we want to find the I component. What we would do is we take away every I component of this matrix. We create a 2 by 2 submatrix using the j and k components, and what we do is we would cross multiply them. So it would return b times p minus c times n. And that's all in the I direction. We'll do the same thing for the j component. We will lock off all the j components and we create a submatrix of k and I. You'll notice that the submatrix starts at k and then ends in I. So what we would do is, again, we would cross multiply. So that turns into c times m minus a times p. And of course we do the same thing in the k component. We ax all that, we create a submatrix, cross multiply, so we get a times n minus b times m. That's all in the k direction. That's all for this time. I hope you learned a lot. All our brains just got a little bit bigger. Next time we'll be going over partial derivatives.